All right, this begins lesson number 6, two-sample test. Let me go ahead and tell you what's going to happen here. First of all, I think this is probably the most challenging lesson aside from lesson number 2. I think lesson number 6 and lesson number 2 will kind of be in a tight battle for which is the most challenging. I'm going to throw a lot of stuff at you that's going to be very complex. Just give me the opportunity to teach it to you and then make a connection, close the gap, if you will, between a pretty challenging concept and making it pretty easy. I hope using Stack Crunch and technology, because these calculations, like for degrees of freedom and we get into pooled variances and different things, it can be very complicated. So give me the opportunity to teach you by watching the instructional videos throughout. All right, so what we're going to learn in the next 3 videos, the purpose of this video is to teach you how to compare the means of 2 independent samples, and the goals for the other 2 videos, actually those are reversed, we'll compare means of repeated measures second, and then compare proportions third. So that's coming up in future videos. So two-sample t-test, from 30,000 feet, if you will. We're going to look at independent samples and repeated measures and population proportions. And the final one in the green, the population variances, I'm not going to cover just because I don't think there's enough time in a week to cover all 4. So the first one, again, difference between 2 means. So what we have to consider here is we have 2 population means. So let's say that we, for example, want to compare a quantitative measure over 2 categories. So maybe category A and B. So let's say that we want to compare maybe ACT scores, which is a quantitative variable, over school district A and school district B. So that's our categorical variables. So what we have is we have the notation mu1 equal mu2. So again, the goal is test hypothesis or form a confidence interval for the difference between 2 population means. So for the scenario that I've set up here, mu1 would be the mean ACT score for school district A, and mu2 would be the mean ACT score for school district B. Now, what we do is we collect a sample from each one of these school districts, and for school district A, we would have X bar sub 1, and for school district B, we would have X bar sub 2. So our point estimate for mu1 minus mu2 is X bar 1 minus X bar 2. Now, here's where things get really complicated. Depending on what we know about our standard deviations of our population, if we can assume those to be equal, then we get into one type of test. But if the standard deviations, which again are unknown, are not assumed to be equal, then we get into something called an unpooled t-test. So if sigma 1 and sigma 2 are assumed equal, we conduct what's called a pooled t-test, P-O-O-L-E-D. And if they're not assumed equal, it's unpooled, U-N-P-O-O-L-E-D, okay? Again, I told you it's going to be more complex. But again, pump the brakes, give me an opportunity to teach you this information. So we're going to have, well, this just really summarizes what I just said. If you come down to the bottom and look at the blue boxes, when we assume sigma 1 and sigma 2 are equal, then we use a pooled variance t-test, and not assumed equal, they call it a separate variance t-test. Most people will call that an unpooled t-test. I think we only look at the pooled variance t-test in this class. So the hypotheses are a little different. This annoys me. But this is just standard procedure. It's just something I got to get over. Now let's look at First of all, I want you to look at the far right green box, the two-tailed test. Notice that the null hypothesis has an equal to, like we always have had in hypothesis testing. And notice that the alternative hypothesis has a not equal to, as we've had previously. Now, those are equivalent to testing that mu1 minus mu2 is equal to 0. Because think about it, if mu1 and mu2 are the same number, 5 and 5, then 5 minus 5 is 0. So it's the same thing as testing that mu1 minus mu2 is 0 versus mu1 minus mu2 is not equal to 0. Now here's the confusion. Here's what I don't like. In a lower tail and an upper tail test, the null hypothesis no longer is presented as equal to, for these types of tests only. It's no longer presented as equal to in the lower tail test. Our alternative hypothesis, H1, is less than lower tail, but our null hypothesis is not equal to as we're used to. It's greater than or equal to. For the upper tail test, our alternative hypothesis is greater than, shooting toward the upper tail, but our our null hypothesis is mu1 less than or equal to mu2. So the equivalence statements down below, mu1 minus mu2 greater than or equal to 0 for the lower tail test should make sense. So we just have to keep that in mind. Now, we still have critical regions. We still have p-values. Those things are all calculated using technology, but this gives you kind of a shot from 30,000 feet to tell you where the rejection regions lie. And specifically for a lower tail test and an upper tail test, that all of the rejection region goes in either the lower tail or the upper tail, depending on the test we're conducting. And then two-tail test, we take the alpha and divide it by 2 and put half of it in one tail and half of it in the other tail. We've done this stuff before, so it's going to probably look pretty familiar. So sigma 1 and sigma 2 are going to be unknown. If we assume them to be equal, we have some assumptions, and the main assumption is that the populations are normally distributed, or both sample sizes are at least 30. Here's where it gets ugly, and here's where it gets messy. The pooled variance. I hate to even present this because you're not going to be required to crunch this out by hand. We run into a situation with Stat Crunch where it's all the calculations are done behind the scenes. But if you're a stat math nerd like me, this kind of stuff, it's kind of cool to you. But most people it's not. So anyway, what I want you to see from this is that the pooled variance calculation, the S sub p squared, is complicated. The test statistic is complicated. Takes the point estimate minus what we hypothesize in the null hypothesis, and then it divides by the standard error. What I do want you to see is at the bottom that the degrees of freedom are easy. We add up N1 and N2 and just subtract 2 for the degrees of freedom for this two-sample independent t-test. The confidence interval, same thing. It's complicated. The calculations are complicated, but it still is in the form of a confidence interval we've seen before. The x bar 1 minus x bar 2 is just our point estimate. The t with the alpha over 2, that's our critical value. We've done those before. And then the square root of the variance over 1 over n plus 1 plus 1 over n plus 2, that's just our standard error. So the calculations are more complicated, but again, I'm not going to require you to do these things by hand. I'm going to teach you how to make these calculations using Stat Crunch. So let's just see how one would happen. So here we have a sales, and it looks like we have different places that a product has been placed in the sale or in the store. So they have one, special front, and then one in the aisle. We take the mean of both, so 246.4 is in the special front and 202.3 in the aisle. Now, people that know squat nothing about statistics will say, well, special front did better than in aisle because 246 is bigger than 202. Well, that's true for these 10 measurements, but we want to make a generalization to all of these type of marketing campaigns, all special front versus all in aisle. So we're generalizing to a bigger population here in a broader statement to not only this sales location and these 10 measurements from from each, excuse me, we're wanting to generalize to something bigger. So down the bottom green box, we're assuming both populations are normally distributed because we have a very low sample size, 10 each. We need 30. So if we only have 10, less than 30, we need normally distributed. And we'll test at alpha equal 0.05. So here are all the calculations. The pooled within variance is 1433.92, and the test statistic is 2.6041. Using our critical value, the critical value is plus or minus 2.1009. So since 2.6041 falls outside that bound between the critical values, it falls in the reject region, so we would reject H sub O. So there is a difference in the, there is evidence of difference in the mean, so it does appear that the one marketing strategy is statistically significant and better than the other. Calculating our confidence interval. You can see the calculations down here. So our 95% confidence interval would say that the upfront marketing approach is about 8.5 to somewhere around 79.7 higher than for the in aisle. Now, if that interval was all negative, then we wouldn't conclude that the in aisle was higher. The second mu would be higher. So again, these are just slightly more complicated than the traditional hypothesis testing examples that we've studied previously. Now, if we don't assume equal variances, we get into an unpooled T-test. And again, you know, we assume the populations are normally distributed, and we still need that the sample sizes are at least 30 if we don't have evidence that the populations are normally distributed. These calculations are pretty insane as well. These tests will be done using software. All right, so what I want to do now is take a little different approach. I am going to bump over here, and I am going to dive into demo number 1, lesson 6, and work the first 2 problems only. I'll show you how easy this is with technology, all right? So a recent study found that 64 children who watched a commercial for potato chips featuring a celebrity endorser ate a mean of 39 grams of potato chips. Must have been a pretty impressive celebrity endorser, as compared to a mean of 24 who watched for an alternative food snack. Okay, so we're wanting to see if there's a statistically significant difference. So our so we want to see, assuming the population variances are equal, so that tells me we're going to use a pooled, P-O-O-L-E-D test. Is there evidence that the mean amount of potato chips eaten was significantly higher for children who watched the so what we're going to have to do is we're going to have to look for looks like mu1 is going to be the celebrity endorser. So we need mu1 greater than or equal to mu2. Oh, we're testing. Okay, so this is the one we would use right here, D. Now, let me explain that. Right here, it says, let population 1 be the weights of children from the celebrity endorsed. We want to see is there evidence that the mean amount is higher. So that means that's what we're testing. So H1 has to be higher because, again, as we discussed in the previous video back in lesson number 5, the alternative hypothesis represents what we're testing. So the opposite of that is what we get there. Now, the next thing I want to do is let me jump over here and get StatCrunch. And I'll tell you what, I want to go split screen here, so let me do that. All right, well, shoot. All right, so here we are. So what I want to do here is I want to go in and run stat tstat to sample with summary. Why do I have two samples? Well, I have the celebrity endorsed commercial and the alternative food snack commercial. So sample mean number 1 is going to be 39 compared to a mean of 24. So I had 64 kids in the sample. And it looks like I have 54 who watched the alternative food snack. The standard deviation for celebrity was 21.5. And the standard deviation for the food snack, the alternative food snack, was 12.8. Now, see, from a technical perspective, with a stronger background stats, I guess most people, if I have a standard deviation of 12.8 versus 21.5, I don't know how we assume that the variances are equal. But anyway, we're not going to pool, well, we are going to pool our variances. So the default is off, but we want to pool our variances here for some reason. And I want to show our critical value. So I'm going to compute. What is the test statistic? Well, for the test statistic, I'm going to report it to 2 places. So that's going to be this right here, 4.50. What is the p-value? I'm going to get that from the table. So to 3 places, it'd be 0.000. What is the correct decision? Well, our p-value is less than 0.05. So we're going to reject the null. So we're rejecting this, that the mu1 minus mu2 is less than or equal to 0 in lieu of mu1 minus mu2 is greater than 0. So we're going to reject H sub O. So only A or B could be possible. So there is sufficient evidence that the mean was significantly higher for that group of kids. Assuming the population variances are equal, construct a 95% confidence interval. Well, that's going to be easy to do. Go up and do edit, click confidence interval, make sure 95% aligns with what the problem says. and we get a confidence interval of 8 point, what's it want us to do? Two places, so 8.39 to 21.61. Now compare and discuss the results. The confidence interval does not contain 0. So the confidence interval in part B contains, which does not agree with the decision. Well, that's not true. So the confidence interval does not contain 0, which, so part C would be correct. Hold on. Oh, okay. Got tricky here. I got sloppy. Because we conducted a one-tail test, and I posted a video about this 2 lessons ago. I can't believe that this happened, but it did. Even I make mistakes in this and get sloppy. Because it's a one-tail test that we're conducting, the 95% confidence interval won't correspond. I think the title of that video was When Confidence Intervals and Hypothesis Testing Don't Agree. So this is a case where they don't agree and they can't be compared, so the results cannot be compared. Sorry about that, ladies and gentlemen, I got sloppy. Based on the results, if you wanted to increase the consumption of this brand of potato chips, which commercial would you use? Well, I want to use the one with the higher consumption. So choose the commercial with the celebrity endorser, since there's evidence that the mean amount was higher. You might argue that it's slightly unethical, but it's the way business works sometimes.